Okay, Sarah, we were just talking about fine-tuning models with Grid Search CV.
Right. And it's crucial to get the data prep right.
But this section highlights a potential pitfall.
Exactly. We can't use the entire training set to scale our data, and then use that scaled data to evaluate our model parameters. It's like cheating.
Whoa. Cheating? Why?
Because the evaluation data is already used to compute the scaling. The model sees this already seen data, which gives it an unfair advantage.
So, how do we avoid that data leakage?
That's where pipelines come in. They chain pre-processing steps in model training.
Oh, cool. So, like a sequence?
Yeah, you chain operations. First you scale, then you fit the model.
So, how does that fix the problem?
You perform pre-processing on only the training part of the split during cross-validation.
So, the pre-processing happens separately within each cross-validation fold.
That's right. This way, you're not introducing bias from the test set, which is crucial for getting accurate model parameters.
Now, what if we wanted something other than min-max scalar?
There are many scalars. Standard scalar.
Are there any others?
There are. Robust scalar, max-up scalar.
So, is there a best scalar?
It depends on the dataset. Some datasets are more sensitive to outliers.
Okay, so a pipeline is like a recipe, but a recipe where the order of operations is really important.
Exactly. You can mix and match various pre-processing steps and algorithms. It's all about chaining.
That's a smart way to avoid data leakage. Great point, Sarah.
Thank you.
Thanks for the insight, Sarah. I think I get it now. Sarah, remember that data leakage problem we talked about earlier?
Yeah, where we use the whole training set to scale the data before cross-validation.
Exactly. So how do we prevent this when tuning model parameters?
We use pipelines. They chain our pre-processing steps with the model training.
Whoa, pipelines? Like a conveyor belt?
Sort of. Each step in the pipeline, like scaling, gets done in the right order.
Okay, how?
We tell pipeline which steps to take. It runs them sequentially inside the cross-validation loop.
So, you scale the data within the folds?
Precisely. The pipeline ensures the pre-processing steps are only applied to the training part of each fold in cross-validation. No leakage.
So, if I have min-max scalar and SVC, how do I make a pipeline?
Pipeline, scalar, min-max scalar, SVM, SVC.
Wow. So elegant. Now, how does that work with Grid Search CV?
Same way. You pass the pipeline to Grid Search CV.
You just plug in the pipeline directly?
Yeah, and tell Grid Search CV the parameters to search for within the pipeline.
So, we're looking for good parameter values for the scalar and the model.
Exactly. This is amazing for efficiency. You get the best values for both parts.
That's incredible. So, no more leaking.
Exactly. No more cheating our way to good results.
So, are there any trade-offs?
Well, pipelines can be more verbose for simpler tasks. But for complex workflows, they keep the code clear.
Very insightful, Sarah. Thanks for clearing this up.
You're welcome. Pipelines help us build robust and accurate models.
I feel like I'm getting a grip on this.
Glad you are.
I see how powerful pipelines are.
Absolutely. It is great.
So, Sarah, we've established pipelines are essential for avoiding data leakage, but how do we actually tune the parameters inside the pipeline?
That's the key. We need to tell Grid Search CV which parameters belong to which step.
Can you give me a concrete example?
Absolutely. Let's say we have an SVM with the hyperparameters C and gamma. We use min-max scalar to pre-process. To tune them within Grid Search CV, we use a syntax like SVM and SVM.
Whoa. Double underscores? What does that do?
You see, the double underscore tells Grid Search CV that C and gamma are parameters of the SVM step, not the scaling step.
So, the perm_grid is structured differently?
Exactly. We explicitly specify that the C parameter belongs to the SVM step, using SVM instead of just C.
Got it. Can you show me an example?
Sure. Perm_grid equals SVM_C 0.001, 0.01, 0.1, 1, 10, 100, SVM_gamma 0.001, 0.01, 0.1, 110, 100.
Wow.
It's more granular than I expected. So, this process entirely avoids leaking data.
Exactly. Now let's think about a scenario where we apply the idea to feature selection. Imagine a model with completely random data.
A model on random data?
Yeah, a synthetic dataset where the features and target are completely unrelated. This is a way to test the model's resilience.
Okay, and feature selection makes this scenario even more important.
Absolutely. Feature selection on random data might yield a very high cross-validation accuracy, but this doesn't translate into a good model in practice. The model is basically finding patterns that don't exist.
I see. So, we must be cautious about using feature selection with entirely random data, or else we're going to be led down a path of overfitting.
Exactly. It highlights how critical it is to avoid data leakage when using pipelines.
This is such a great point. It's not just about the data, it's about how we interpret the results. Continues. Sarah, you mentioned feature selection can cause problems if we're not careful. Can you elaborate on the feature selection example with the random data?
Absolutely. The feature selection step in the initial example looked for features correlated with the target, but because the data was random, this correlation was coincidental. These random correlations ended up being highly misleading for the test folds.
So, the cross-validation results were inflated because the model was finding patterns where none existed.
Exactly. That's data leakage. The feature selector leaked information about the test set into the training process.
I see. How does a pipeline prevent this?
By making the feature selection part of the cross-validation loop. The pipeline ensures the feature selector is refit for each cross-validation fold, using only the training data for that fold.
So, it's like the feature selection is now reevaluated for each fold without seeing the test data?
Exactly. This is crucial. The pipeline ensures each fold is treated independently.
That's a much cleaner way to do feature selection. Can you walk me through the pipeline's internal workings?
Well, the pipeline class chains fit_transform and transform methods together. Think of it as the data is passed through each step.
So, for each fold, select percentile is refit on the training data, and then ridge is fit on the process data?
Precisely. The ridge model doesn't see the test set until the pipeline predicts on the transform data.
Wow.
That's a very careful process. So, without the pipeline, you could potentially be misled by spurious correlations.
Definitely. It's like a mechanic working on a car. You need the correct parts from the correct section to avoid confusion.
The whole concept of pipelines and cross-validation seems to be about very deliberate and meticulous data handling.
It is, Jane. It really is about extracting the true patterns and not just the patterns that seem apparent due to chance. This is essential in any machine learning model, isn't it?
Absolutely, Sarah. It is very important, and the pipeline makes this so much more straightforward.
It's critical to understand the potential for leakage, especially when working with feature selection. The pipeline ensures the evaluation is unbiased, and you are only relying on the training data for that fold.
Thanks for clarifying the pipeline structure.
I get the importance of this now.
Glad to help. Now let's think about situations when the initial features aren't random but still aren't strongly predictive. How might this change our approach?
Sarah, you were talking about pipelines making data handling so much more organized. Now, let's say I want to make a pipeline that's a bit more involved.
Yeah, Jane. There's make_pipeline for that. It makes constructing pipelines easier, especially when you have a bunch of steps in a row.
So, it's like a shortcut for building complex pipelines?
Exactly. It automatically names the steps for you, which is super helpful.
So, no more typing out names for each step.
Exactly, which can also help avoid typing errors. It's great for scaling up.
How does it work under the hood?
Make_pipeline takes all the estimators you give it and creates a pipeline object. It's essentially shorthand.
Interesting. Let's say I want to use PCA after scaling. How does that look?
You just put standard scalar and PCA inside make_pipeline. The names are taken automatically.
Wow.
So, no extra code for naming steps, cool.
Right. Now accessing the PCA step is also simpler. Using named_steps, PCA.
What if I had multiple scalars?
It'll differentiate. It'll use naming conventions so you can still access each step you know.
Sometimes this automatic naming can get a bit much if you have a really long pipeline, right?
True, you might want to use the explicit pipeline construction for better readability when the naming gets complex. You always have the option to name things explicitly.
So, what about using named underscore steps in a grid search?
The same approach. You can use named underscore steps within the grid search to access attributes of specific steps inside your pipeline.
Okay, so in a grid search, we are going to be working on the names assigned.
Correct. Just use named underscore steps, your underscore step underscore name, to get at the values you want.
So it's a way of extracting data from a very specific step in the pipeline.
Yes, like if you wanted the coefficients from a linear model or principal components extracted by PCA.
So make underscore pipeline is really handy, especially when you have to interact with specific parts of your pipeline.
Exactly. It's a nice trade-off between convenience and maintainability.
Good point, Sarah.
I'm starting to see this whole process as a sophisticated orchestra, and these pipelines are the conductor.
Well, Jane, every piece of software or hardware really relies on some kind of design. I think of the pipelines as the design of the process.
Interesting. I'm starting to see that pipelines are useful, and make underscore pipeline speeds things up significantly. Sarah, let's talk about using these pipelines within more involved tuning strategies like grid searches.
Sure, Jane. We can use make underscore pipeline directly in Grid Search CV. It's really efficient, especially for combining pre-processing steps and models.
So, it's a shortcut for a complex process.
Exactly. Let's say we want to tune the regularization strength of a logistic regression model after scaling the data. We can do that in one clean pipeline.
How does this look in code?
We build the pipeline first, then create a parameter grid. For example, using logistic regression, the tuning parameter is C.
How do we specify it then?
We have to use the named underscore steps with a special key that indicates which step to affect.
Wait, can you give an example?
Sure. Logistic regression. That's how we tell Grid Search CV to adjust the C parameter of the logistic regression step inside the pipeline.
So, it's like telling it to target a particular part of the pipeline.
Exactly. This approach makes tuning really straightforward and avoids getting lost in parameter names.
So, how do we extract the coefficients?
We use the best underscore estimator underscore to access the best model, then named underscore steps, logistic regression, .coef underscore.
Wow, super clear. So, are there trade-offs?
Yes. Manual creation is more control, more readable for super long and complex models. But make underscore pipeline makes it efficient if you're just tuning a few steps.
What if we had something like polynomial features, too?
You can totally include polynomial features in the pre-processing steps of your pipeline. Make underscore pipeline handles the nesting for you.
This is like a powerful toolkit.
It is. We can build sophisticated workflows efficiently without sacrificing readability. It's a huge time saver when building complex models, but you still have complete control when you need it.
This is super exciting, Sarah. Thanks for explaining this in detail.
You're welcome, Jane. This allows you to really focus on what matters, the design of your model.
Sarah, we were discussing using pipelines for grid searches, so awesome. This Boston housing example, how did that choose polynomial features?
Well, Jane, the idea is that sometimes linear models don't capture the underlying relationship in the data well. Adding polynomial terms can fit curves, allowing for a better prediction.
Interesting. The heat map in this example, what does that tell us?
The darker the color, the better the model performed. You see these peaks where particular combinations of polynomial degree and alpha produce high cross-validation scores.
So, the degree 2 and alpha 10 combination is super accurate?
Not necessarily the best, just the best within that limited grid search. There might be even better scores elsewhere in the larger parameter space.
But doesn't this require evaluating many different models?
Absolutely, you are right. This exhaustive search approach is very powerful, but becomes computationally expensive when there are many parameters. This is a trade-off.
So is there a better approach?
Yes. Randomized search CV. It samples random combinations of parameters, and you define the number of iterations.
Making sure I understand. So instead of checking every possibility, you just sample?
Exactly. This is faster and potentially enough to find good parameters, especially when searching a huge space.
But are more complex pipelines always better?
Not necessarily, Jane. It can add more complexity if the benefits don't outweigh the cost. You need to consider the dataset and potential overfitting.
Makes sense. Are there any use cases that are obviously too complex or ill-suited for pipelines?
Yes. Think about datasets with many features and interactions where the search space is enormous.
You're right. It's a balancing act, tuning efficiency versus potential gains. Thanks, Sarah.
You're welcome, Jane. Finding that balance is part of the art of machine learning.
Sarah, the last example, it's intriguing. We're searching not only for the best model parameters but also for the best preprocessing.
Exactly, Jane. This is a step up from just optimizing the model itself. We're exploring the combination of preprocessing and the model.
So, with the cancer data, why standard scaler for SVC but not for random forest?
SVC is sensitive to feature scaling. Standard scaler helps to ensure features have similar ranges, which is important for SVC's performance, especially with RBF kernels. Random forest isn't as affected by this.
That makes sense. But the search space seems enormous. Isn't this too many possibilities?
Potentially, but often the results are worth the effort. Some of the best ML solutions are those where the steps are tuned precisely to the dataset, and that takes a little exploration.
So, there's a delicate balance between exhaustively checking everything and getting a sensible answer quickly.
Precisely. And random search CV can help. We sample random combinations, potentially finding good solutions without checking every single possibility. Saves time.
But how do we know when the gains don't outweigh the extra steps?
It's a case-by-case assessment. The dataset and models need consideration. If the gains in accuracy are modest, the added complexity might not be worth it.
Great point. Sarah, what about real-world examples? Have you seen this multi-step approach yield substantial benefits?
Definitely. In a project I worked on, a multi-step pipeline with different scaling methods and different model types increased accuracy considerably. That's the beauty of ML. Different strategies for different needs.
So, the pipeline approach is powerful for a wide range of scenarios, but not always appropriate, right?
Absolutely. A truly monstrous feature space or a dataset that's inherently simple to model might not see that big of a gain from such detailed exploration. Understanding the problem domain helps to make the right choices.
Right.
Sometimes simpler is better. Makes complete sense.
It's about finding the optimal balance. Thanks for these insightful questions.
Sarah, you've been championing complex pipelines, but this final chunk feels like a gentle nudge towards simplicity.
Exactly, Jane. Sometimes the most effective models are the ones with the fewest moving parts. Simplicity often translates to better performance and interpretability.
So, what constitutes a necessary component in a machine learning pipeline? How do we know when to cut out the extras?
Well, let's imagine we have a model for predicting customer churn. We started with a complex pipeline, but when we pared it down, we saw almost identical performance.
Aha.
That's a good illustration. Does this approach always work? Or is there a subjective element?
It's usually a combination of a methodical process of evaluation and experience. It's like when you get a really great recipe. You can start tweaking and adding stuff, but the original simple recipe is often the most delicious.
What if these extra components actually improve things?
Well, there is a trade-off. That's where the balance comes in. If the improvement is marginal compared to the additional complexity, sometimes simplicity wins out.
A good model builds on the basic elements and avoids over-engineering, right?
Exactly. Overly intricate pipelines can hide underlying problems, especially issues with data or model assumptions. And yes, it's often about building the simplest model to effectively achieve desired outcomes.
Sarah, let's be practical. Can you give us an example of where simplifying a pipeline actually improved results?
Sure. In a project analyzing credit risk, we initially used a very complex feature engineering pipeline. After simplification and removing irrelevant components, accuracy improved.
So, simplification isn't always about sacrificing performance. It can actually enhance it.
Absolutely. It forces us to really think critically about which features and processes truly matter.
Perfect.
This makes a lot of sense. Sarah, what are your concluding thoughts on building effective machine learning models?
A balanced approach is key. Combining rigorous evaluation, experience, and a little bit of trial and error is paramount to building robust and accurate models.
Absolutely. Sarah, thanks for these insightful lessons.
My pleasure, Jane. It's been a truly enlightening discussion.
This has been a great podcast. We've covered some serious ground.
It has.
To further your machine learning journey, subscribe to our podcast. We'll be delving into more advanced topics in the future. We hope you have learned a lot.
Thank you, Jane. We're excited to see you all again on our next show.
Thanks for listening. Until next time, keep exploring the fascinating world of machine learning.
See you then.